Go ahead.
Yeah. So I wanted to take the topic about cryptography for packaging. So recently I was working on changing the signing keys that we had for one of our project, and that led me into finding quite many things how we use these GPG tools or keys for signing the packages and getting to know about the validity of the packages. So I would start with very basic. So I had kept a small agenda for this. So we can start with the basics of cryptography, which is the symmetric cryptography. Then I would move into asymmetric cryptography, which we currently use. And then the tools that we are using for asymmetric cryptography, and some of the demos for how encryption, hashing, and digital signature works. And then moving on to, I will create a small Go package and Go binary. I will package it using RPM and then create a repository and then share the repository with, if I have time, I can share it on internet, or I can locally share it and show how one can release their own binaries to RPM or Debian based systems. Okay, so to start with, so this is the symmetric key. So in symmetric key cryptography, usually what we do is we only have one key, and the same key is used for encryption and decryption. So you have a document and you encrypt that document with this one key, and you get an encrypted document, and you have to share this document with someone. So this is the first person. So this person wants to share this document with someone over an insecure network. So he shares this document over insecure network to uh, the person B, and now the person B again decrypts that document with the key and then gets the document. The only issue with this thing is both the persons need to meet physically or over a secure network to share their keys, because if any one of those don't have the key, then they cannot decrypt the messages. So they have to come somewhere and get the same keys, the symmetric keys, and then the document could be decrypted. So to overcome this, asymmetric key cryptography was introduced, and this has a pair of keys. So these two exist as a pair of keys. So if you encrypt using a public key, you can decrypt that using the private key, and vice versa. So we can currently look most of the like SSH keys that we have, the signing keys that we use to sign our packages are all asymmetric keys. So we share the public key with the world, and we never share the private key. Whenever someone signs the document with the public key and it gives to us, only we can see what is written in that document. So the process looks something similar to this. So this is the document, and we encrypt this document using the public key. So now in this case, this is the person A, and he wants to send the document to person B. Before even sending this, the person B would say that, okay, this is my public key. Whenever you have to send something, please encrypt it with my public key and then send it over an insecure network. So somewhere they have exchanged their public keys. So uh, uh, and this can be also not that secure network that is there. So they exchange their public keys, and now because only B has his own public key, so no one can see the documents that are encrypted by B's public key. So now what happens is A signs these documents using the B's public key, and these are the encrypted documents, and he sends it over the insecure network. And after he sends it over insecure network, then it receives to A, and now A wants to see that uh, only A can see that what is inside that document. So he will decrypt it with its private key, and then he can retrieve back the same document that was signed here. So this is a public key or asymmetric encryption that That's it. So there always exists a pair of keys, and the document is signed by a public key, which is available to everyone. And then once the document is sent to someone, he checks with his private key, and if the keys match, then it can actually decrypt the document. So this is called as encryption, where we have a document, we encrypt it using someone's public key and then send it over the network, and the one who possesses a private key can only decrypt it. So now there comes a concept of digital signatures. So currently here what we are doing is we are signing using public key. In digital signatures, we would encrypt it using a private key. So this would be useful because if I have to validate that this particular message has come from me, I would have to say that only this key is something that I possess and no one else possesses. So if I encrypt it using this key, so I have a document and I encrypt it using my private key, and I also share the document because everyone has the public key. So anyone can encrypt this document and they will get whatever is written into that document. So now we share the actual document here, and we also share the encrypted document. So when someone wants to check the identity, that was it actually the person who possesses the private key has encrypted this. So what he will do is he will check the public key. He will decrypt this using the public key, and he will get a document, and he will check both documents. If they both documents match, then we can say, okay, so this person had signed this, that's why it is matching. And if he cannot decrypt using any of his public key, then we are sure that this person didn't sign this and it has come from somewhere. So the only the difference in digital signature is it is signed by a private key, and it is used to authenticate the identity uh, of someone. So in using currently in TLS or any communication forms, the server signs a message with its private key and sends it over to the clients or the browsers. And now the browsers know the public key of the server. So they decrypt those message and checks the actual message and the encrypt actual message and the decrypted message. If both of them matches, then they can say that the server that they are communicating to is a valid one because uh, they were able to decrypt the message with their public keys. So uh, that we could say is a digital signature whenever we will sign it with the private key. So moving forward, there is also a discussion for hashing, which I need to do for one of the thing that we will see ahead. So hashing is something like you have a big document and you want to verify that this document has changed or not. So what you could do is you could pass the complete document through a hash function, and you will get a small checksum around 256 characters or whatever function that you have used. According to that, you will get a checksum. And if the document has changed anytime, the checksum will also change with that. So I can show you a demo for this, and this can be used for if there is a binary that you can't tell that has changed or has haven't changed. So we can actually identify that this particular binary changed or it hasn't changed. So I can show you the demo for this. So okay. So now I would go to show first demo for what hashing is, and then I would move to GPG tools and show the demo for encryption and decryption and how we can sign the messages. Uh, yeah. Okay, so this is an Docker environment that I'm using, and it has Debian 10 running. So mostly I will have to update it. Yes, so usually the hashing, if we have to do hashing, the GNU provides us few tools. So I will use some of them. So MD5 sum is one of them, MD5 sum, and other one is SHA-256 sum. So these are both hashing algorithms or hashing functions, and we can see the changes in it. So I can create a small document. And so if I have to say that MD5 sum of this document, so it will give me the current checksum of this document. So this says that currently this particular hash is the checksum. And if I change it or I create a new document with the same name, and then again ask MD5 sum, are the contents same? And it will say that the contents of both the files are same. So usually we can use it to verify the contents of any file and even binaries. So I can show an example where we have a binary, and if we change the binary, the checksums also change. So this is a very small function, and I could say that here hello world I would print, and I can build it using go build hello.go. So the binary was created, and if we run this, and we can see hello world is created. But this is a binary, and we cannot actually say is this binary created by this particular code or not. So what we could do is we could check MD5 sum of this binary, and we get a number, a hash for that. And after that, we can again we can move this to say backup, and again and again create the binary. I'm getting an echo. Okay. And again create the binary. So now I got this binary. So now I know that this was the previous binary and this is the current binary, and I have to change. Is there anything that has changed in the code? So I can just do MD5 sum for the current binary and MD5 sum for the old binary that I have. And if we compare that, these two are same. And now I change some code inside that. Now, okay, so now the binary that would be created would be different. So I will create another binary for this. And if we run it, it will say now hello Mars. And the previous binary used to say hello world. And if I check the MD5 sum of the new binary that was created and the old binary that was there, so both have changed. Now, without looking at the running code, we can say a particular binary was created by this code or not. So usually what people do is they have a code this running code, and they have to see, is this binary, this particular binary created by this this code. So what they do is they create a new binary uh, from the source code, and they check its MD5 sum and also check the MD5 sum of the binary that we have that was already there. And if both match, then we can say uh, the uh, the same code, source code that someone has shared was used to create this binary. So this is also useful while sharing the documents among someone, so that if we share a large document around GB 4 to 5 GB, and we want to make sure that this document is not tampered with. So usually ISOs for operating systems has a checksum there. So you can download the complete ISO and then you verify that is it the same ISO that this that CentOS says that. So they will give you a checksum and you can verify the checksum with that ISO, and if the checksum matches, then you are sure that this ISO was not tampered. So no one has tampered the ISO, and this is as provided by the CentOS team. Okay, so now I guess now we can move to GPG, and this is the main tool that we use for signing the keys, creating keys, then also to signing our repos. So I can start with a simple example where we create a small GPG key. So if we only do GPG double dash help, we could get all the options that it provides. And currently I want to generate a complete key for this. So now it asks me that what type of key I have to create. So RS, so these are like public key and private key pairs. So I said currently I want to create an RSA key, and it also asks what is the key size that we require. So I could say 3072 works for me. Right. So this is the validity of the key. So you can create a key which will expire on this particular time. So currently, if you don't keep any expiry, then it won't expire anytime until you revoke it yourself. So I can say I don't need an expiry. So this will be valid until I revoke it. It again asks me to confirm. And now it asks me the information of some who has created the binary. So you can do some comments, then okay. So I will keep an passphrase for my key so that even if the key is stolen, uh, I don't have to worry until he breaks this password. So now if you see, the key has been created and this is the fingerprint for the key. So we can see GPG double dash list dash keys. So it tells us that the key with Pranav, and this is the uh, email ID or verifier that I have used. And it also tells me that how many keys are there. If you have more than one keys, you will get multiple outputs here. So currently now I have created the key and I have to share this key with the public key with someone. So I have to export the public key so that I can exchange communication between two channels. So I would say that export the key with the name Pranav, and this, and please put it into the public.key directory. So now I will get public key here. So this is my public key, and this I would share on the internet. So everyone can verify me. So what I could do is I will create another Docker container here. So okay, this is running. So actually here also it asks for few keys that are from the CentOS repo, the Rocky repo. Okay, so I will paste the public key here. So now I have shared, currently I copied this public key from this Docker container and I have pasted it into this Docker container so that they both can interact with each other. So I also have to say that GPG to tell that import this particular key. And now if you do GPG double dash list dash keys, and you will see this fingerprint also here, which is similar to the one that was here. So if even if someone had shared you a public key and you want to verify, it is a good practice to verify what is his fingerprint. So like I share my public key with someone and then he calls me and asks me what is my fingerprint, and then I tells him that this is the fingerprint of my private key, and so he verifies it with his uh, the public key that he has imported, and once the fingerprint matches, then you can say okay that this particular public key was actually created from this private key. So now an encrypted communication we can encrypt messages from the public key and give it the uh, to the user to check for decrypt it. Okay, so I can create a file for just to show how encryption we can we can do using GPG. So, this was the file. So I know now I have to encrypt this file, and double dash armor is for us. I have to encrypt in ASCII format, and for file name I will say hello.txt. It asks me, okay, really want to, yeah. So now if you check signed encrypted key, encrypted message is created here. So this is my hello.txt, and this particular encrypted message was created. So now I can send this message to the one who has the private key, and only someone who has the private key can read this message and no one else. So I will, from this Docker container, Rocky's Docker container, I will go to Debian Docker container. I will create this same file. Usually we pass it over network and then get this, but for uh, for this demo, we can create this document. And now we have to just say decrypt this particular message what it was. So we can say hello.txt.asc, and then because only we have the private keys password, we can input the private keys password to decrypt it. And okay, so now you can see the hello.txt was created here, which has the same message that was in this hello.txt, and we didn't have that file there. We just uh, took this encrypted message and then decrypted it here using GPG's decrypt function, and we were able to decrypt the messages. So there is one more thing that we can do is, as I said about digital signatures, we can also sign using this private key. So currently only on this machine I have the private key, and here I only have the public key. So I can sign some messages here. So I will create another file, sg demo.txt, and I can sign it using the detach sign method, detach sign argument, and this will create this will create one file which is with the sign, which is .asc. So this is the digital signature that I had signed using my private key. And now if someone wants to verify me, I will send him two documents. One is the actual document, and the other one is the signed document, this one. So that they know that only I can sign this using my private key, and they can verify it using my public key. So now I can actually create this file here. So this would be something like I'm sending this particular file. So this was a signed message, and this is the signature that was created. And if I have to verify it, I can just say GPG verify this, and now it says, okay, this signature was made by at this particular time with this particular private key, and it says that it is a good signature from who has signed this key. And he knows that because in this list I have my uh, the public key is inside this. So if you see, yes, authorized signature authorities which actually sign those certificates that we see on the SSL when we do HTTPS. This you can see there, while you click on that lock button, you can see who is the signing authority for this particular certificate. So currently these are self-signed keys. So I created my own key and then I signed those key and then I'm sharing it. Okay. So now now we know that how the signing works. So just to summarize it, we can create a private key and a public key pair. We distribute our public keys to everyone, and they add those public keys into their own machines. And if I encrypt a message using my uh, private key and then send the message, actual message, and the encrypted message, and if they are able to decrypt it using my public key, then they are sure that this particular message was signed by me, and they verify the identity for that. So we need this while distributing packages. So packages are a few binaries, and we want to trust the entity that is creating the packages. And to establish that trust, they share their public key. They sign those packages with their private key, and we can check are those packages signed by their private key, and also they sign the repos so that if any tampering happens in that packages, so if someone, a middleman, changes the repos, the binaries, and we know that now this particular binary was changed because it won't have the same signature that was created. So we would currently now go into building and small hello world app, and then creating an RPM out of it so that we can share with the CentOS or RHEL based systems, and then create also sign it and then create a repo for that. So I will take one of the example that we have here. I will just modify it. And usually whenever we build Go applications, only a binary is created, and that binary is if you create for Linux, and that is compatible with all the Linux versions. So I will create a binary on this Debian machine and then try to install using RPM on this particular machine. So to create a binary, you would have to go build and hello.go. So now the binary is running and we can see the output of that, and we can move that binary to slash user bin so that okay, so we can move that to bin so that you can follow it from anywhere, even if you where did it happen? So build hello.go, hello to slash user bin. Okay, now it is there in the bin, and now if we only run it from anywhere, we can get this because this particular directory is in my path. So now I have to create an RPM out of it. So I found a tool FPM which can create RPM Debians and all the necessary packages that we usually have, even Node packages and Python packages. So usually if you have to create an RPM with C++, you have to get the RPM build and then write the RPM spec file, and after that create it will create an RPM, and there are rules that you have to follow, like where the binary should sit and where the configuration file should sit, and that is all defined in your RPM spec. But because Go package only has one binary, so it would be easy for us to directly go with and wrapper around RPM build, and this will also give us uh, quite easy one command line from where we can build a binary. So for running this FPM, we have an dependency with Ruby, Squash FS tools, and of course to build RPM, we also need RPM to be installed. So I will install this on this machine. Mm. And this is a Ruby package. So using gem, we will install the FPM. Okay. So now I have to package it for RPM. So what I will do is, this is a command that I have copied and I can actually directly paste it here. So I want to create an RPM. If someone want to create an DBM, they can put DEB here, and we can also specify like what is the version, what is the description, who is building the package, what is the website for this particular package, and other comments. So currently for demo purposes, I am ignoring those and just putting the things that are necessary for now. So, and I can say go hello, and okay, and just the path to the binary that was there. Okay, so it says that it has created the binary. So this is the binary it has created. And this binary has the hello binary. This RPM has the hello binary that was there. So now before sharing this, we have to create an RPM repository so that anyone can get these binaries, and also we have to sign those repositories so that they also verify that this particular binary was shared by me. So currently for signing the repositories, we have to first uh, get the public key. So this is the public key that we would need for the repository, so that if anyone wants to verify what was it created by me, so they can just uh, I can just share it with them, and then they will get to know this was shared by me. And to you won't need to import currently here. Okay. So this here now we have to sign the RPM package that we have. So this is the RPM package, and RPM provides us an double dash add sign uh, or RPM sign binary that is there. So I will just copy this and tell him that where the binary is. So go hello is the binary that is there. Okay, so this will sign this binary with the private key. Okay, GPG no such file. Which GPG? Okay, I guess I have to create another soft link for this GPG2 version. Okay, so now I'm signing this using my private key. So this now it doesn't say anything that it is signed, and if we have to see RPM dash Q, this for so it says digest signature not okay because I haven't imported my public key. So I will import my public key first, and now it says the digest signature is okay. So because this particular machine didn't have my public key and it wasn't able to uh, read this binary signature. So once I imported the public key, now it says the signature is okay. Now I have a I have a binary which is signed. Now I have to create a repository out of this binary so that I can share it with the RPM based machines. So for this, I will create a new directory, and inside that directory, I will keep this RPM, and there is an create repo tool that RPM provides so that we create a repository out of these RPMs. So I will first install that. Install create repo. So this is the slide that I will. So I have installed the create repo, and I will also create a directory so that I keep all my RPMs at this particular directory. So npd, and I paste my RPMs into this. Okay. So once I paste it, now I have to just say that I have to create repository out of this particular directory. And so now it has created a repository for me. If you go inside this, we have just put only one RPM. Now it has created a repo data, and this repo data has all the metadata for this binary. So if we get this repo data.xml, it has this repo data for all the RPMs, and it also creates a small SQLite database. So these are a few of the small SQLite database, and it also has the metadata for those. So if you change anything in this binary now, then you will have to regenerate this metadata. Otherwise, the checksum won't match. And so if you see there, these are the checksums, and if you change anything in this file, this checksum won't match, and the someone who is installing from this repository would face an errors. So now I can do is I will, because this is the repo data, I will also have to sign this repo data with my key so that the metadata is also signed, and anyone if has to double re-verify that was this metadata signed by the public key, the private key, and they can verify that. So I will similar to the previously we had signed using the private key, we will just sign this particular directory with the private key now. RPMs repo data. Okay, and this will create a dot ASC this signed copy of the particular repo data that is there. So now this is ready to be deployed. So the thing that we had done are to verify that this the identity of the provider was. So we had signed the RPMs using the private key, and also signed the repo data using the private key. So if any of these change, the if anyone wants to tamper this, then they have to possess my private key, and then they will have to tamper something and again re-upload with my private key. Otherwise they can't tamper until they have my private key. So now to install this, we will have to import the similar to what we have imported here, the public key. So we have to import this public key, but currently we have already imported it, and we have to create dot repo directory uh, in our package managers directory, so that we can download it from that repo. So I will create repo data. So it's in etc yum.d. You can say custom, and it should end with dot repo. And okay, so now here we just say that this is a custom repo data. Here we have to actually give the URL from where the repository is hosted. After that, we have to say that for this machine, we have to enable this repository, and the GPG key is to say that uh, this particular repo should be checked with GPG key, public GPG key, so that we trust that identity of someone who is sharing this. Mm, yes. Okay, it's yum.repos.pm custom. Okay, we have some time. So I can actually deploy this on one of the servers, and we can download it from there. So slash so this is the Docker container is sharing this particular directory so that I can create a server from here, and then we can download it. So to create a server, because I don't have a server running up there, I can use ngrok to that to create a local tunnel. Ngrok. Okay. So this will create a local tunnel at this particular uh, this particular uh, host name. So and I will start a Python server from here on my local host. Okay, so now if I go to this directory, the one that engineer had shown me. So I have shared it again. Okay, so this is the slash opt that we have shared, I guess, because I don't have a SSL certificate. So we have to give this particular path to our uh, from where we have to download. So this is the file. So the base URL is from where we have to download, and now I can give the path https. I guess it will have everything. So we have to say that this is the uh, resource from where I will get the repo data and binary. And now if I have, because I know what is the name of the repo, the name of my package, it is say go dash hello. So I can just say yum install go dash hello. Now it should search there, and now it got that package that is currently hosted here. And I will say, okay, I have to install it. So, okay, it installs, but it fails for GPG check. Public key for go-hello.rpm is not installed. Okay. I will again try to import this public key here. Or I will say RPM import. And try to install it. Now it says completed because that particular key I haven't included in my RPM, the public key. That's why it gave me error that this GPG key check was failed. Now I added that key into my RPM so that RPM also knows that this particular key is the one that will be used to check this package, and I was able to install using RPM. So if anyone wants to create any packages, so I have actually listed down these steps. So they can actually create a small binary, Go binary, and then deploy it on the web anywhere, wherever the file hosting is available. So I guess that's it what I had to share. Hmm. So you have any questions you can ask me.